The next example asks us to look at a situation where you've got three charges: a negative charge with a charge of negative 8 microcoulombs, a positive charge with a charge of plus 3, and then another negative charge, Q3. And example 2 asks us to find the force on Q3. The first thing to recognize is that the forces exerted on Q3 by these two charges will be in opposite directions, so we have to be careful of our signs. These opposite charges will attract, so Q2 will pull Q3 this way, but like charges repel, so Q1 will push the charge that way. So we have to calculate the difference between those two forces and be careful of our signs. And it's not obvious just looking at it which one will exert the greater force. So we'll make the decision. Let's call towards the right positive in terms of the positive x direction, so that charge 1 exerts a positive force and charge 3 exerts a negative force towards the left, so that we can keep track of those two forces. So we'll write these two forces as, say, let's call one of the forces force 1, 3, and the other force 2, 3. So force 1, 3 is equal to, we'll go ahead and write it as K now, just instead of 1 over 4 pi epsilon naught, just so we're used to both versions of that. The charge is 8 microcoulombs, and we don't actually have to worry about the sign. I just said that I was taking care of the sign myself, so we'll leave that sign out. We'll just put 8 microcoulombs times the charge of Q3, which is 4 microcoulombs, divided by the distance between them, which we see this is 0.3 and this is 0.2. The total distance between 1 and 3 is 0.5 meters. And we have to remember to square that. So that's all we need in order to compute that. If we bring up our calculator, we've got 8 times 10 to the negative 6 coulombs times 4 times 10 to the negative 6 coulombs divided by 0.5 squared equals, and then we multiply that by K, which is 8.99 times 10 to the 9th, 10 to the 9th equals, well, that doesn't seem right. I think I screwed that up. There's no back button on this calculator. Let's start again. 8 microcoulombs times 4 microcoulombs equals, divided by 0.5 squared equals, oh, I think I divided instead of multiplied. We're using K, which is 1 over 4 pi epsilon naught, so we're going to multiply that times the value for K, which is 8.99 times 10 to the 9th. There we go. 1.15. What? 1.15 newtons, because this is a force. So the force that 1 exerts on 3 is, what was that number? That was 1.15 newtons to the right. 1.15 newtons. That away. Now let's calculate the force that 2 exerts on 3. That's going to be equal to K times the charge of 2, which is 3 microcoulombs, times the charge of 3, which is 4 microcoulombs, divided by the distance between them squared. They are closer. They are only 0.2 meters apart. And that is going to be equal to what? Clear. 3 times 10 to the negative 6 coulombs times 4 times 10 to the negative 6 coulombs equals, divided by 0.2 meters squared equals, times 8.99 times 10 to the 9th equals 2.69. We'll go ahead and round that up to 2.7 newtons to the left, because Q2 and Q3 are opposite charges, so Q2 is pulling Q3 towards the left. So the net force is equal to F23 minus F13, which is equal to 2.7 minus 1.15, which is equal to 1.55 newtons. Which direction? Oh, sorry, I lost track of my cursor there for a second. What was it now? 1.55 newtons to the left, which is the answer that we get from the book. So doing these problems is no different than doing Newton's law of gravitation problems. It's a simple matter of using Coulomb's law, keeping track of what direction your vectors are, and being careful with your units and your signs. What we'll look at next is a problem where the forces are not on a direct line from one another, but the forces are in 2 dimensions, and so we have to use vector math to find that force.